Today we're going to learn what is the fundamental theorem of calculus. This is very, very important. It has two parts. We'll pretty much only deal with the second part of it for now. Later on we'll go back. And evaluating definite integrals, because that's what the second part of the fundamental theorem of calculus shows us how to do. So what do we already know? We already know if you evaluate an indefinite integral, which means it's an integral without limits of integration. If you evaluate an indefinite integral, you just get the antiderivative of that function. So I'll just denote that by capital F, where capital F is the antiderivative of f. That's kind of, I mean, not formally, but that's kind of the first part of the fundamental theorem of calculus. The indefinite integral gives you the antiderivative, or an antiderivative. Remember, because the plus c, the c could be any number. Okay, that's very good. We'll get more in detail with that later. But the second part of the fundamental theorem of calculus deals with definite integrals. So what if we have a definite integral? Well, first, just so you know, suppose that capital F of x is the antiderivative for f of x. That's nothing new. We just said that up here. So if you take the derivative of this, you get that. That's all that it's saying. So if you have the antiderivative, or you know how to get the antiderivative, then you can do something. So suppose that capital F is the antiderivative of f of x. Then here's the whopper. The whopper? What? The integral, which represents the area between the curve and the x-axis, the integral from a to b of f of x with respect to x is equal to, what? This is going to be crazy. Is equal to the antiderivative minus the antiderivative? What? And then you plug in first b, then a. Oh, what? It's backwards. Okay, so like this is what people are going to have a problem with. When you read this, you go from a to b. That's in the forwards direction. You know, a is usually smaller, b is usually larger. If it's the other way around, then the area would be negative because it's directional area. However, when you plug it in, you do the bigger one minus the smaller one. That's just like distance. You can think of it like, oh, what's the distance between 3 and 4? Well, you take 4 minus 3, right? Hopefully that makes sense. It's kind of like that. I used to imagine like this is a little snake and it strikes, whatever. I don't know. I'm not even going to. That's done. So this is how you evaluate definite integrals. You get the antiderivative, and then you plug in the top part, the bigger value. Usually, it's not necessarily the bigger value. You plug in the top part, and then you subtract when you plug in the bottom part. What? You need to see an example. All right. This is super important. Super important. You need to know this. It's how you evaluate definite integrals. So let's take a look at a very simple example. So here we go. It says example 1. So we want to know what is the definite integral from 1 to 4 of 2x raised to the negative 3 over 2. Well, we can get the antiderivative of this very easily. So that's what we're going to do first. So this is how you write this stuff. If you get the antiderivative, that means you're adding 2 over 2 to this. So I do that first. Maybe I'll do it in red. I'll definitely do it in red. Okay. Plus 2 over 2, that gives me negative 1/2. Yeah? Because if I add 2 over, okay. And then I divide by negative 1 over 2, or I multiply by negative 2 over 1, right? I flip the second one and I multiply. And then I keep that coefficient out in front. Okay, so what is, well, and then I evaluate that. This is like an evaluation line. I don't know. This is how you write this. It's just notation. From 1 to 4. So what does that mean? Well, I have the antiderivative. So I can write out What am I writing? I write, well, I'm doing this part. I have to plug in the top part, the top number, that's the 4. So here, negative 2 times 2 is negative 4. And then instead of x, I plug in the 4. And then I get the negative 1/2 minus, again it's negative, so I got a negative 4. And instead of the x, I plug in the 1. So I plug in the 1 there. And it's still to the negative 1/2. And this will equal to, well, let's just simplify each step. Negative 4, that's over the square root of 4. This changes to plus 4, right? Because the square root of 1 is 1. Alright, well, what is that? That is negative 4 over 2 plus 4, which equals negative 2 plus 4, which equals to 2. Positive 2. So what does that mean? That means the area underneath this function from 1 to 4 is 2. Comes out to be 2. Amazing. This is beautiful. So the area under that function is 2 units squared. 2 square units. Oh, that's nice. That's it, really. Now I'm just going to show you some examples. Do you guys understand?
Yeah, we understand. It's pretty easy.
Why, I'm teaching a mouse? Well, what is the, okay. Next video, just more examples. We're just using that. You get the antiderivative, you plug in top, you minus, when you plug in the bottom.